Hey guys, welcome back to another Maths Made Easy video with A-Level Maths. We're starting A2 here, A2 Mechanics to be specific. So we're going to start with moments. So I've got a bunch of the tricky questions from the textbook, and then at the very end I have a very special treat for you. It's an extra hard question that you won't have found anywhere else. So please make sure you at least check that out if you find the first few questions easy. Before we get started, I would like to just ask you guys if you could subscribe and like if you've ever found any of my videos useful, because most people haven't subscribed or liked, and it does really help out the channel. But without further ado, let's talk about moments. So a moment is a very interesting thing indeed. It is a turning force. So it is found by doing force times distance. And the distance is from something called a pivot. So I want you to imagine a door for a second. When you have a door, you have the hinges on one side, normally, well, depending on which way you come from the door anyway, you have the hinges on one side. That is the pivot point, because if you notice, the door pivots around that hinge, i.e. it moves around that hinge. Now, why are moments useful? Well, you may notice that the door handle is always put far away from a door. So if I draw a door here, you might have the hinges on this side, and the door handle will always be on the opposite side to it. And the reason for that is, well, I want you to try something next time you open a door, which is a very strange sentence, I admit. Normally you open the door from this side and it's super easy. I want you to try pushing the door open somewhere along here. So maybe not right on the hinge, but right there. You might notice it's a hell of a lot trickier. The reason for that is because the D is the distance from the pivot point. The further away you are from that pivot point, the greater the turning force. And the greater the force, that means the greater the acceleration. It means the door opens more easily, because you don't need to have this force be as large in order to open the door. Whereas if you reduce D, then F has to increase. You have to put more effort in order to open the door. And this is used everywhere in terms of engineering, but also real life. So things like wrenches and spanners, well, you might have like a nut or a bolt that you want to kind of unscrew. Doing it with your hands is very hard because your distance is basically zero from the pivot point. But if you use a wrench or a spanner, that increases the distance that you are away from the pivot point. Now, of course, this is A-level maths. It's not quite as simple as that. It is also important to note that F and D, when you're talking about moments, are perpendicular to one another. So, for example, if I have a pivot point and I have a straight line and I'm pushing it up 10 newtons and this is 2 meters away, then I just do 10 times 2. Because these are perpendicular to one another. But in most cases, we're going to have something that looks like this. So we have our pivot point and then we have like an angle here where we're going to have to now work out the perpendicular component of the 10 Newton force. But again, we've had practice with this in year 12 and we're going to get practice with it now. So moving on to the very tricky questions. Again, I've picked some of the hardest questions from each of these from each of the chapters in the textbook, but at the very end I have a very hard question for you that should really test your understanding. So here we have a drawbridge and it's being inclined at an angle of theta, where theta is between 0 and 90, which makes sense because the drawbridge will be fully up here. You don't want to go beyond that because there's no point. And the actual drawbridge itself is a uniform rod with a weight of 8,000 newtons. Uniform means that the weight acts at the very middle of the beam. So in other words, either side of this, let's say if it's a 10 meter long beam, the first part is 5 meters and the second part is 5 meters as well, because it's right in the middle. A horizontal force of magnitude 6,000 newtons is applied. Given that the drawbridge is rising, so that is a very important part, I'm going to underline it right here. Prove that tan theta is greater than 2/3. So what do I do? Well, remember what my first step is in any mechanics question is to draw a damn diagram. So I'm going to draw something that's much larger, and we have theta here, we have those 8,000 newtons, and we have 6,000 newtons acting up here. Okay, so that is our initial diagram, which looks exactly the same as this, but what else can we add? Well, as I mentioned, we are going to be looking at the moments, force times distance, and if you remember what I said, they must be perpendicular to each other. The distance is going to be the drawbridge itself, because it's the length of the drawbridge. So what we need to do is make both of these forces perpendicular to the drawbridge. So if I do that, well, first things first, I can do something like this. So we have a perpendicular component here of that 6,000 Newton force. But wait, do we actually know the angle? Well, if you look, this is a giant Z angle, an alternate angle. So that is also going to be theta. So the perpendicular component will be 6,000, and in this case, well, it's going to be opposite over hypotenuse, so it'll be sine theta. So remember, when you're doing things like this, when you're resolving forces in a plane, you need to be able to work out which side is which. So this is opposite the angle. If you're using opposite and we're using hypotenuse, it would be sine. Okay, and what about when you have a weight like this? Well, there's another geometrical trick. We're going to split it like this. And the angle here is also going to be theta. Now in this case, we want the perpendicular side, which is this side over here. So that's adjacent to theta, and we have the hypotenuse. So that is going to be 8,000 cos theta. Now what's my pivot point? Well, my pivot point, it seems fairly clear, is this point down here, because the drawbridge is going to go around that point. So if you imagine, I hold that drawbridge there and it turns around the point here. So again, if we look at the original diagram, we're pulling the drawbridge up. This point down here will never ever move. It's hinged to the ground. And you need to use your logic there to decide where the actual hinge point is, or the pivot point. Perfect. So now here's the next thing about moments, is they don't act left, right, up and down. They act clockwise and anti-clockwise. So if I were to work out the clockwise moments, we would still do force times distance, don't you worry. And then we're also going to have anti-clockwise moments, okay? And again, that still equals force times distance, but how do you tell? And this is another problem that a lot of students have. So here's my top tip on doing this. Now, what I do is I use a pen to represent the beam, the rod, the drawbridge, whatever it is. I use a pen. Now, if I use that pen and I put it here, my pivot point will be this point of the pen here. So now I'm going to ask myself, the 6,000 newtons is pushing it up like this. So which way would the pen move? Will it move clockwise or anti-clockwise? Now, again, on video, it's going to be inverted for you. So I need you to do this for yourself with a pen in your hand. Because to me, that will move clockwise. So the clockwise moments is the 6,000 Newton force is clockwise. Another way to look at it is if I look at it on the diagram, if this force here is pulling it up, the drawbridge is going to move like this, which is clockwise. So whichever way you need to do it, you need to imagine it. Either have your pen, put it on the paper and move to see which way, if it moves clockwise or anti-clockwise from your perspective. Likewise, if I use a different colour, if I have that 8,000 newtons, again, what's it going to do? Well, it's going to push this rod down, right? It's going to push it down. So in other words, it will move that way. It will move anti-clockwise. So that 8,000 newtons force is going to be anti-clockwise for the moments. So again, two options. One, put a pen on the page itself, lay it flat, and then move it around to literally see. Or go back to the original diagram and imagine what would happen if that's the only force we have. So if it's 6,000 newtons, it would just move up like this. If it's just the 8,000 newtons, it will move downwards. So now what we need to do is do the calculation. So we have 6,000 sine theta, because remember we want the perpendicular component, times, well, what is the length of the drawbridge? Well, if I look at the actual question, it doesn't tell me what the length of the drawbridge is. So I'm just going to say the length of the drawbridge is D, because I don't know what it is. Of drawbridge. So 6,000 sine theta times D. So in other words, it would be 6,000 D sine theta. Cool. Then what about the anti-clockwise moment? Well, it was going to be 8,000 cos theta. And what about the length of the drawbridge? Well, again, it's not the length of the drawbridge here. It's only a fraction of it. Well, because it's a uniform rod, remember what I said. the weight acts as if it's in the middle of the drawbridge. So it's halfway along. So if I want to call this whole length d, then half of it should be d over 2. Which, if I cancel out 8,000 then divided by 2, would be 4,000 d cos theta. Okay, so I've gotten these two things now. I've got 4,000 d cos theta. I've got 6,000 d sine theta. How does that help me? Well, if we go back to the question, it says prove that tan theta is greater than 2 over 3. Now, I'm thinking, well, sine over cos is tan. Okay, the inequality is a bit interesting as well. Well, let's have a look. It says, given that the drawbridge is rising. If it's rising, it means we are not in equilibrium. Now, equilibrium does come up a bit later, but hopefully you can see, if this is rising, then it means the clockwise moment has to be bigger than the anti-clockwise moment, because otherwise it will be going down or staying still. So you can even think of it like you're lifting something. If this is 40 newtons, and I put a force here and I say the object is going upwards, then you know that the force upwards has to be greater than 40 newtons because we're lifting it. The same thing works for moments. Because the drawbridge is going clockwise, the clockwise moment has to be bigger than the anti-clockwise moment. So in other words, 6,000 d sine theta has to be greater than 4,000 d cos theta. And of course, the first thing I'm going to do is I'm going to cancel out d from both sides. I'm going to divide both sides by cos theta. Why? Because I know that my answer has tan theta in it. The only way to get tan is sine over cos. So if I divide both sides by cos theta, I get 6,000. Sine over cos is tan theta is greater than 4,000. Divide both sides by 6,000 and we get tan theta is greater than, well, okay, let's do it fully. 6,000, cross out the zeros, and then it's going to be greater than 2/3 for 5 marks. And again, in terms of for 5 marks, I don't think that's too, in terms of the length of the question, it's not too bad, but I do acknowledge that that is not the easiest question in the world. But hopefully that all makes sense. I do think the maths looks pretty cool. Like, look at all this stuff, it looks really interesting. But if you want to do engineering, this is the kind of stuff you have to do. So I hope you found that interesting. The next thing we need to talk about is equilibrium. So equilibrium is a part of this question here. And what does it mean? Well, there are 2 conditions for equilibrium now, not just one. The first one is there is no resultant force, i.e. the forces going up and down are equal and opposite to each other. Forces going left and right are equal and opposite to each other. But now there's no resultant moment. In other words, clockwise moments equal the anti-clockwise moments. So if anything's ever in equilibrium, both of these things have to be true. I have seen 1-mark questions that say something like, for an object to be in equilibrium, there needs to be no resultant force, name the other condition. Or they just say name both conditions. Or they say, what does it mean when an object's in equilibrium? 1 mark. If you don't say both of these, you get 0. Anything along those lines. So let's have a look-see, shall we? This is a very different situation to the drawbridge from the first question that we did. So there are some things that are slightly different. But let's read through it. A non-uniform rod. So non-uniform means that the weight will not be directly at the centre. It will be either to the left or to the right. It'll be somewhere. But we don't really care. It's in total, this is a length of 25 meters. And there's 2 supports C and D. The centre of mass of the rod D is 10 meters away from A. Okay. Particle of weight W newtons is attached to the rod at point E, where E is x meters from A. The rod remains in equilibrium, and the magnitude of the reaction at C is 5 times the magnitude of the reaction at D. Here's what I'm going to do. I like to annotate my diagrams. So if the total length is 25, well, we have 6 plus 5, that's 11. So that means the middle bit must be 25 minus 11, must be 14 meters. It then tells me the centre of mass is 10 meters from A, so it's probably going to be somewhere over here, which is going to be 80 newtons. Remember, the centre of mass is where the weight is said to be taken from. Anything else? It also says that there's these 2 supports. So remember your contact forces from year 12. when you have something resting on something else, they both have to have contact forces or reaction forces or whatever you want to call them. Particle of weight W newtons is attached to the rod at point E, where E is x meters from A. I have no idea where that is, so I'm just going to call it W over here. The rod remains in equilibrium, and the magnitude of the reaction at C is 5 times the magnitude of the reaction at D. Show that this is true. So now I'm going to draw my proper diagram. So, the reason why I like annotating the question and then drawing another diagram is if I make any mistakes or I make something look a bit weird, it doesn't really make a difference. So, what do I mean by this? Well, now they're telling me that the magnitude of the reaction at C is 5 times bigger than at D. So instead of having two variables, I could say that the reaction at D is R and the reaction at C is 5R. There you go, I've eliminated one variable already, which is very nice. The rest of that I'm actually quite happy with. So what would I do in this situation? Well, in this situation, and whenever you come across a moments question like this, where you have a flat rod, whether it's suspended from steel cables or if it's supported by two supports, you always want to resolve in two ways. You are definitely going to be working out moments, and you are definitely going to be resolving vertically. And I want to make that really, really, really clear. Whenever I come across students that struggle with mechanics in general, whether it's year 12, whether it's year 13, whatever, whether it's physics, is they don't create equations. They try and look at this and say, well, I have 3 unknowns, what am I meant to do? Well, I have 2 unknowns, what am I meant to do? What you're meant to do is resolve, always. So every single moments question, which looks like this, again, whether it's suspended from 2 cables or whether it's supported, is I always do 2 things before I even read the question, before I even know what they're talking about. So once I've labelled it, here's what I do. The first thing I do is I resolve vertically. So if I look at the forces vertically, well, pointing upwards, I have 5R and R. So we have 5R plus R, and it equals the forces downwards, which is 80 newtons plus W. And if you're wondering why that's the case, well, remember, it's in equilibrium, which means the forces up and down are equal and opposite to each other, because otherwise this rod would be going upwards or downwards. So that gives me 6R equals 80 plus W. I don't know why, actually I do know why I wrote it like that. And then R is equal to 80 plus W over 6. Again, that could be useful in a second. I don't know yet. I'm going to be honest with you. I have no idea if it's going to be useful or not. The second thing you're going to do is you will be taking moments. You will do this 100% of the time in moments questions. You'll also do this in 99.9% of the questions. Do both always. Now the question is, what do I want to call my pivot? And the answer is whatever you want. I'm going to say that one more time. You can pick any point to be your pivot. It does not make a difference. So, what are the considerations? Well, the first thing is, I know all of my distances from point A, because it tells me them. It's 6 meters from here, there's 14 meters between C and D, so there's 20 between these. I know all of the distances. And then again, X meters from A. If I wanted to take C as my pivot, for example, then I would need to write X minus 6 in order to work out the distance. So again, you can take anything, but bear in mind your distances will be different depending on where you take your moments from. But again, it's your choice. The other thing to consider is your unknowns. Now, if hypothetically I took my pivot as C, what is the distance of RC from C? 0. So in other words, if I did take moments about C, my moment would be RC times 0, which is 0, which makes sense. If I'm holding the pivot point and I'm trying to push it, it's not going to turn because I'm pushing on the pivot point. In the same way that if you put your hand on the hinges of your doors and you try and push just the hinge, the door's not going to open because your moment is 0. So 2 considerations. 1, where are your distances from? If they're from A, it makes sense to do your moments about A. 2, if you have an unknown that you think won't cancel, then you should take moments about that point. But again, there's no reason why you couldn't take moments about both and see if you can create some equations. Now, I already have a way of substituting in R, so I'm not even going to treat this as an unknown because I know it equals 80 plus W over 6. I couldn't even read my own handwriting there for a second. 6. So I'm going to take moments about R, and I'm going to take clockwise as positive. So it doesn't really make a difference because we know they're equal to each other. But if I start with the clockwise moments, well, if again I put my finger on that point there, or I put my pen on the page, RC is going to push it up, so anti-clockwise. RD is going to push it anti-clockwise. Then the 80 Newton force and the W force will push it clockwise. So again, I hope that makes sense. Let's have a look. So what do we know? Well, the force, the 80 Newtons force, we know that, but do we know the distance? I actually can't remember. So the centre of mass is 10 meters from A, so I know that the distance from here to the 80 Newtons force is 10 meters. So I'm going to put that in, 80 times 10, plus, in fact I'll put it in brackets, W is X meters from A, so we're going to have W times X, equals, because again it equals the anti-clockwise moments, 5R times 6, so that's 30R, plus R times 6 plus 14, because the total distance from A to D is 6 plus 14 is 20, so plus 20R. Okay, so we have 800 plus WX equals 50 times R. And if we have a look at what the answer is trying to tell me, it's trying to tell me that we need to show that W equals. So if I rearrange this for W, do I want to do this now? Well, we'll see. Let's just rearrange it now. I can see that if I divide both sides by X, my answer doesn't look quite correct because we have 25 minus 3X there. So what I'm going to do instead is I'm now going to substitute in for R 80 plus W over 6. Why? Because in my answer, there is no R present there. So I know I have to eliminate R. But there is a W in my answer. So let's do that. We have WX equals 50 times 80 plus W over 6. So 80 plus W over 6 minus 800. I think what I want to do is times everything by 6. So we have 6WX. So why am I doing that? It's because I want to get rid of the over 6 in the answer. Yep. But that's the main reason why I was doing that. So 8 times 6 is 48. And then just add the 2 zeros on. So 4,800 now. Yeah. Expand the brackets. 6WX equals 50 times that, so it'll be 40, and then add 2 zeros. Yes. Yeah, 40, and then add 2 more zeros on. Yeah, that's fine. So ignore that comma. Plus 50W minus 4,800. And again, looking back at the answer, we have 400 over 25 minus 3x. Good. So we need to move all the W's together. Which would be better? It kind of depends. It looks like... Okay, here's how I'm actually going to show you how to do this. So 50W minus 800, because 4,000 minus 4,800. In my answer, the 400 is positive, so I'm going to move the number to the left and the WX to the right. So we have 800 equals 50W minus 6WX. If I look at the answer, I'm actually very close. We have 400, we have 800. They have 25, we have 50. They have 3, we have 6. So if I divide everything by 2, you get 400 equals 25w minus 3wx. Let's factorize out a w on the right hand side. Divide it down, and we are done. Perfect. So again, a recap of what we've just done. Equilibrium now means that the vertical and horizontal forces are all equal, and the clockwise and anti-clockwise moments are equal as well. And again, remember my top tip. Make sure you resolve in both ways. This is going to come in big when you do all of your mechanics preparation. So I want you to resolve vertically, horizontally if applicable, and use moments. If you get those three things done, you will always find a solution to the question. And if you, let's say we did this resolving and we couldn't find a solution, then what do? I take moments about a different point, try and eliminate something. That's what you need to do continuously. And again, remember this point here. If I take moments about a point that has a force on it, that force is basically nothing for the moments. So do keep that in mind. The next thing about moments is something called the point of tipping. So point of tipping means that it's about to start rotating or turning, tilting, whatever you want to call it, but hasn't quite yet. And it says that it's on the point of tipping about n. What does that mean? Well, it means that this whole thing is about to go this way or that way. So what does it mean about the moments here? Well, first of all, we know that there's going to be tension in both of these points here. And the key part is, if it's on the point of tilting about n, it means that the tension at m, or the force at m, the resultant force, whatever it is, so it could be a resultant force, equals 0. Now, if you think about this, if we're about to start lifting this beam, then the tension is going to go to 0, right? If I start lifting that beam, the tension's no longer existent, right? It doesn't exist because it's 0, because it goes slack. So all you need to remember is that if it's on the point of tipping about one point, it means all of the other reaction forces or tensions or whatever it is go to 0. So here we have a non-uniform beam of mass m and length 8a, hangs horizontally in equilibrium from two wires m and n, where p to m is a, q to n is 2a, so that means the middle bit is going to be everything left over, which is 5a. The centre of mass of the movement is on the point O. A particle of mass 3/4 m is placed at q. So 3/4 of m. And the beam is now on the point of tipping. So as you can imagine, this weight on the other side is pulling the beam to go upwards. It's just about to start lifting, which means the tension in this part of the cable is now 0. And we need to show that O to N is 3/2A. So here, hopefully it's somewhat obvious, but we're going to be resolving, and I'm going to take clockwise positive about point N. Now here's the key thing about tilting, is the beam is still in equilibrium. So that means that the clockwise moment still equals the anti-clockwise moments because the beam has not started tilting yet. It's about to. So it's about to start doing this, but since it's about to, it's still in equilibrium. It's just the tension that's gone to 0. So let's see, taking moments about that point, we have clockwise and anti-clockwise moments. Now, if I'm taking that as this is clockwise, again, if I put my finger on a pen here, so again, that's what's happening. Q is over here. If I push that down, it's going to be clockwise. Again, put your finger on the screen right now and push the rod downwards at Q. You'll find that the whole rod will go upwards in a clockwise motion. So that force there is 3/4 mg, and we're timesing it by 2a. Perfect. And now what other force do we have? Well, there is a weight somewhere. There's a centre of mass. And it says the mass is just m, so g. But we do not know where this length is. In fact, oh, sorry, my apologies. it tells me it's at O, but we don't know what that distance is because the question actually says we need to find that distance. So I'm just going to call that distance between O and N, I'm going to call it X. Cool. So that equals mgx. So what can I do first? Well, the first thing I'm going to do is I'm going to cancel out m and g from both sides. And I'm left with, well, 2 times 3/4 would be 3 over 2a. So 3 over 2a equals x for 3 marks. That is why I do love moments, by the way. I do love mechanics because you get quite a few marks for not doing too much work. But again, you need to be very careful with everything, okay? Define all your distances. Now, part B. The particle is removed and replaced at the midpoint of the beam, and the beam remains in equilibrium. So it's no longer on the point of tipping, okay? So somewhere in the middle over here is going to be our 3/4 mg weight. Without, weight. Find the tension of the wire at point N in terms of M. So that's what we're going to do now. I'm going to take moments about point M. So again, resolving around point M. And why am I doing that? Do you remember from the previous part? Why am I doing that? Because I don't know what this tension is. This tension is no longer 0. So because I don't know it, and I don't care about it, because I want the tension at N, I'm just going to take moments about this point, which means the tension at the moment from that tension is 0. So if you want, you can even put Tm times 0 is nothing. Cool. So if I'm taking moments around this point, the clockwise moments would be this force, and this would be the anti-clockwise moments. And remember, we've gotten rid of this force. So let's do that, shall we? So we have 3/4 mg first. And what is the distance? Well, the distance, if you notice, so we have A here, we have 2A here. That means the middle part is 3A. Actually, sorry, it even tells us. So it's at the midpoint. So that distance is 4A. So I'm going to take away 1A, which gives me 3A. I like to put it in brackets just to be super clear. Then we have mg, which is at point O. And how do I want to define this distance? Well, so I know that the distance from N is x, so that's 3 over 2a. So what I might do is remove that for a second. That's 3 over 2a. The distance here, well, we have 2a on this side, a on this side, and the full thing is 8a. So 8a minus 2a minus a gives me 5a. So in other words, the distance from M to O is 5a minus 3 over 2a. So that would be, what, 10 over 2a minus 3 over 2a. So that would be 7 over 2a. And that equals, finally, the tension at N times 5a. Because a is in every single term, I'm going to cancel those out right now. There is nothing else that's in every single term, but if you notice, it says find the magnitude in terms of m. So we actually have everything we need now. So if I want to expand this, we have, expand this. 9 over 4 mg plus 7 over 2 mg equals 5, the tension at N. And all I need to do is combine these two now. So that would be 14 over 4. 14 plus that would be 23 over 4 mg equals 5 Tn. Divide both sides by 5. We get 23 over 20. Again, you can use a calculator to verify. Equals Tn, and I'm done. Now, the question I sometimes get is, well, is this in terms of m if we have m and g? But remember, the value for g is a constant. It's 9.8. So we don't need to actually include that. We can leave that in terms of m and g because m is the only variable. That's the key point here. And now, as promised, we're going to go on to the super hard question now. And as promised, an extra hard question that you probably haven't seen before. So we have a man, a very well-drawn man, and a dog. So we have a uniform plank. So again, remember that means the mass of 30 kilograms is directly in the middle of this beam. It is supported by 2 pivots. So again, that means we have 2 reaction forces, RA, and I'm just going to call this R. That might bite me in the butt in a second. But they give us all the distances, all the lengths, which is very nice. A man whose mass is 80 kilos, so that means his weight is 80 G, is standing on the plank 2 meters from A when his dog steps on the plank here. We do not seem to know the mass of the dog, so I'm going to call it mg. Given that the plank remains in equilibrium, remember, and that the magnitude of the forces exerted are equal. Perfect. That means I can get rid of the A here. They are both R. We need to calculate a bunch of stuff. Now, we need to calculate the magnitude of the force exerted on the plank by the pivot at A. So that means we're trying to work out the resultant force, right, the R. We need to find the dog's mass, and I'm going to, this last bit is a bit of a theory based. So remember what I said. The first thing I would do, because it's in equilibrium, is I'm going to resolve vertically first, even if it doesn't get me the answer. So resolving vertically. Taking upwards as positive, we have R plus R, so we have 2R, equals the mass of the man, the mass of the plank, and the mass of the dog. So 80 plus 30 is 110G plus mg. And I notice I can't really do anything, right? I can't finish that. So the next thing we need to do is we need to take moments. Now we have to decide where we want to take moments from. We could take it from the man, we could take it from A, we could take it from this pivot here, we could take it from the dog, and actually anywhere in between. Now, we need to be very careful with this. We need to think. If I'm imagining this, my question is asking me to work out R. So I want to work out R. So that means I don't really want to eliminate R, right? So I don't want to do it from point A or from here because I want R. I know the mass of the man, so it doesn't make sense to take pivots around that. But I don't know the mass of the dog. So I'm going to take moments about B because it's the only unknown that I don't care about. That's my logic. So we're going to take moments about B, and once again, I like to take clockwise as positive, just because I do. Once again, put your finger on point B or use your pen, whatever you want to do. Which ones will make it go clockwise? Well, it's going to be the 2 R's will make it go clockwise, so let's start with those. This one here will be R times 2, so that would be 2R. And then it would be 2, 6, 8, it would be 8R as well. Equals the anti-clockwise moments. So the first anti-clockwise moment is the mass of the actual plank. And if you remember, it's a uniform plank, so it's halfway along. If the full beam is 8 meters long, then that will be halfway, it'll be 4 meters. So we're going to do 4 times 30 G, so that's 120 Gs. Plus the mass of the dude, so that's 6 times 80. And yeah, so that'd be 480 Gs. Anything else I've missed? Don't think so. So that would be 10R equals, add those together, it's 600 G. And I know that there may be a temptation to just kind of divide by 10 and do all that stuff. In fact, no, that's perfect, yeah. So R is just equal to 60G. That's part A done. For 5 marks. It's pretty good, right? 5 marks for 3 lines of working out. Part B, find the dog's mass. Well, it's a good thing I did that resolving, because I have an equation for the dog's mass in terms of R, and I now know what R is. Isn't that convenient? So, for part B, we can just sub that straight in. 2 times 60G equals 110G plus mg. Again, I'm going to cancel out the G's, which makes sense because we're dealing with mass here. We have 120 equals 110 plus m, so we have 10 equals m. And that's another 3 marks in 3 lines of working out. So in 6 lines of working out, we've gotten 8 marks. It's pretty good. It's pretty good. So, for part C, it asks a wordy question. Explain how the force exerted on the plank by each of the pivots would change if the dog was heavier and the plank was on the point of tilting. So we've made this bigger. Well, now here's the thing. This is why this question's extra difficult. Because when people see on the point of tilting, they'll say, no reaction. Which is true, but no reaction where? Here's where you need to use your imagination. If I weigh, so I've got two pivots here and here, right? If I'm weighing down this side more, it's not going to turn about point A. This thing will turn like this, right? If you notice, it would come off the pivot at A, it'd stop touching the pivot at A, but it would still touch the pivot next to the dog. So the no reaction only happens at one of the, well, only one of the pivot points will still have a reaction force. So there will be no reaction at A. That is one mark. I think everyone should be able to get 1 out of 2 on this question. Because again, all that is imagining what's happening. If the mass of the dog increases, then it doesn't make sense for the pivot here to no longer touch. In fact, I'm just going to call this point C. It doesn't make sense that the pivot at point C would no longer touch. Because then what's it rotating around? It's not rotating around the dog. So, pivot at C, pivot at A. If I weigh down this side more, it stops touching the pivot at A, which means there'll no longer be a reaction force at A. So, why is that only 1 out of 2? Because it says by each of the pivots. The other pivot, well, point C, what will happen? Well, again, when I said it's on the point of tilting, we still have equilibrium because it's not moving yet. So if I no longer have this, if I resolve this vertically again, I would get R equals all of the masses added together. So 80g plus 30g plus mg. That is going to be bigger than 2R equals this, because of course it will, right? So the reaction at B, or C in this case, increases. Because it will have the weight of the dog, the weight of the man, and the weight of the plank all on one pivot. And that's the really, really key thing. So I know I went through some very tricky questions. I would have recommended, if you wanted to use this video for revision, going through the textbook first, maybe looking at a few of the questions just so you have a vague idea. But these are some of the hardest questions that you can find. Again, if you want some more questions that are more like this, where they become trickier and trickier, do let me know. I have hundreds of questions on all of the mechanics and stats topics that are a lot harder than the ones in the textbook, so do let me know if you want that. But again, if you found anything useful in this video or any of my other videos, please consider liking and subscribing because it really does help me out. But without further ado, I'll see you in the next one.